we just defined the Gaussian mixture model, or mixture of Gaussians, and the probability density function under this type of model was a convex combination of individual Gaussian densities. And now if you want to use this type of density function for, say, for clustering or for just density estimation, then you need to be able to infer the parameters of this distribution. You know, you're given some data and you want to infer the parameters or estimate the parameters, maybe maximum likelihood or map estimates. And it turns out, since it's a mixture model, it turns out that this is quite hard to do, you know, in general, but that EM gives you a very pleasant way to actually try to get a decent estimate of these. And so in this video, we're going to derive, or maybe it might take more than one video, EM for the Gaussian mixture model. So the parameters in this case, I was just mentioning that we want to infer our theta is a vector consisting of this vector alpha, PMF for Z, and all of the mu's. Let's just write the set of mu's and the set of covariance matrices C. So we've got all these parameters, and let's remind ourselves what was EM. So in this, I'm going to take the approach of you could use the general form of EM, which I described, and that would be, you know, forming that function Q of theta and theta t, which was the conditional expectation of the log of the probability of x and z given x, and then maximize that. But I'm going to take the alternative approach for exponential families in this video, primarily because I wanted to illustrate how that method is used, and also because it's actually a little bit simpler in this problem, so it'll save us a little bit of work. So let's remind ourselves what that formulation of EM looked like for exponential families. So we had the expectation with respect to theta t minus 1 of the ith sufficient statistic, and that was a function of x and z, given that x equals little x, equaled the expectation using theta as the parameter of just the ith sufficient statistic. And these were random variables z here. That was theta t, sorry. So at the general step of the iteration, we need to solve for theta t with theta t minus 1 already known or computed. So let's write this. So let's modify this to make it. Let's make this just a general theta. You know, to simplify our notation a little bit, let's say that's theta, and this is theta 0. Just to make the notation a little simpler. Okay, so the first thing we need to do is to establish, if we're going to use this formulation, is to establish that this thing is, in fact, right, we have this model, but we need to establish that this is an exponential family, and so we can figure out what these sufficient statistics are. So first, let's consider the case when we just have a single, you know, a single data point x and a single hidden variable z for that x. And let's show that this thing, actually it's this right here, that this is an exponential family. So I could just, maybe I can just copy and paste. Let's just copy that. Copy and paste. So let's show that this is an exponential family. So this, let's write out what first. Well, first we want to the z and the x are the variables here, and the parameters are the alpha, mu, and c. So to get it to look like an exponential family, we want to get stuff up in an exponent. We want it to get like e to the something, and we want it to get to look like a dot product between the variables and or some functions of the variables and some functions of the parameters. So let's make this look like e to the something. And we can write, because alpha k equals e to the log alpha k, this equals e to the zk log alpha k. And let's just now write the definition here of the normal density, 1 over the square root of the determinant of 2 pi c, ck, that is, exp e, that's e to the minus 1/2 x minus mu k transpose c inverse x minus mu k. And so actually I think it's going to be a little bit easier here. If we, instead of using c, that was ck, if we instead use the precision matrix, which is defined as the inverse of the covariance matrix. If nothing else, it'll save us from having to write C inverse over and over again. So this becomes lambda k, and this becomes, since the determinant of the inverse is 1 over the determinant, we get this. Okay, so let's start pulling together some things. Now, if we want to put this in the exponent, so this is proportional, we can forget about the 2 pi because it does not depend on x and z. So proportionality will drop out that 2 pi, and we can get, let's pull everything together now. Oh, and I forgot the important zk up here. So this is to the zk, right? And then we also have a zk in here. There's a zk in the exponent. It's important. So what do we get? Well, actually, I guess we can go ahead and let's go ahead and move this product inside. The product of exponentials equals the e to the sum. So we get the sum zk alpha k, log alpha k, and then we get, let's go ahead and do this one first. Oh, actually, let's do this one here. So this becomes 1/2. We move this into the exponent. We get 1/2, actually, zk over 2 log determinant of lambda k minus zk over 2. And let's go ahead and multiply this part out. So this is x transpose x minus 2 mu k transpose. Actually, let me go ahead and what do I want to do here? Yeah, let's do minus 2 mu k transpose lambda k x plus mu k transpose mu k. All of that stuff. Let's switch colors now, since this is starting to get way too green. So now, what are we trying to do? Let's step back for a second and remember what we're trying to do. We're trying to get it to look like e to the, the form of an exponential family is e to the theta transpose s of x and z times h of x and z divided by some normalizing constant. So we want to get this exponent to look like a dot product between parameters, stuff which actually this is going to be, in general, this is going to be a function of theta. So some function g of theta, some vector valued function, and some functions of x and z only. So how can we do that? Well, here we have, so this part's looking good. We got zk here, and this part's looking pretty good. So actually, I think I left out. Yeah, this is the sum. Yeah, so hopefully that's clear. This is the sum over all, this whole expression here. K from 1 to m. So this first part's looking pretty good for the z's. For the z's alone. Over here, we're going to have z's combined with x's. and x's combined with themselves. So let's first let's take care of this little part here. Simplify this up a little bit, because it doesn't matter what this function of alpha, what the function of the parameters is. We can simplify this. Let's just call it zk beta k, where beta k is going to be log alpha k plus 1/2 log determinant of lambda k. Okay, so that's good. And then we have over here minus, let's go ahead and pull out the half, I guess. One half zk. And then we have xx transpose, so that's important. Oh, wait, shoot. I left out, sorry, that was a mistake. I left out the lambda k in here. I'm sure you noticed my mistake, so this should have been x transpose lambda k x minus that, and then I also left it out here. Mu k transpose lambda k mu k. Okay, there we go. So we get zk, and now let's do a little trick here with this. So this equals, this is called, well, I don't know what it's called, but I call it the trace trick. So this is a scalar quantity. X transpose lambda kx is a scalar. So it's equal to its trace. The trace, remember, of a matrix is the sum of the diagonal elements. So the trace of any scalar is of course equal to itself. And there's a special property of the trace, which is that, so if you think of each of these x, lambda k, and x as matrices. These are just special, like, this is a n by or d by 1 matrix. The trace of any three matrices, let me put this as an aside here, the trace of A, B, and C, we can cyclically rotate these inside the trace. So that equals the trace of, C, A, B. So we can apply that here, and we get that this equals the trace of x transpose lambda k. So let's apply that in this sum here. We're going to get the sum, and we're going to get trace. We can pull the zk inside the trace. So this is trace is linear. Zk x transpose lambda k. Okay. Right. So that's looking good, and then we have, so that's looking good because the trace, so this is another thing about the trace to note, that the trace, this is another fact, where should I put it? I'll put it down here. The trace of matrices A and B is essentially a dot product. It's the dot product of all the elements of A with all the elements of B. If you think of A as a vector and B as a vector, then it's the dot product of those vectors. So in other words, this is the sum over all I and j going from 1 to D or whatever the dimension of these matrices is, Ai, j, Bij, where these are the entries of those matrices. And so therefore, this is essentially a dot product of the elements of this matrix. And these elements of this matrix are pairs xi, xj. And so that's looking good. Okay, I'm going to have to stop there. There's going to be more to come, of course, but I have to stop there for this video out of time, and we'll finish up this calculation for EM for the Gaussian mixture model.